My research is in compile time analysis for program understanding and program transformation. So we analyze programs during the translation process. After you write a program in a programming language, it goes through a translator that basically emits the code that the machine actually executes. And it's during that translation phase that we try to understand the meaning of various constructs in the program to help us build tools for program understanding and also to help us transform the programs so that they can execute faster and better. And my group has currently 4 different projects underway, and what I hope to do is to try to give you a little bit of intuition as to the kinds of software tools that we want to use these analyses in, and a little bit of intuition about the kinds of experimentation that we do as part of our analysis process. So how do we keep our work relevant to the real world, I guess, is the way I would phrase that. So first I want to talk to you about our largest project and most long-term project, which is to try to tell something about the side effects of programs written in the language called C, which is a very popular programming language in the community. And the kinds of information that I'm talking about has direct application to 3 different kinds of software tools. So the first kind of tool I want to mention is the compiler itself. So we want to know information about the way variables are defined or stored into or written, and then later on in the program fetched from or used. When we're looking at a compiler that's trying to target code for parallel machines, we're usually looking at numerical operations, and we want to be able to tell if we store into one element in an array, later on in the program, we want to tell where that value might be fetched from the array, because there's a certain temporal relationship we have to maintain. We call it a dependence, to make sure that in the translated program, the store into that value, the store of that value into the array happens before the fetch from that array, so we get the right value. Another area in which we've been doing a lot of work is to handle side effects that are, one might say, invisible or at least obfuscated by the use of pointers. So here we have a store indirectly through a pointer variable. You can think of it as a pseudonym. So the actual variable whose value is being altered in this assignment statement is not visible by looking at the code. Instead, we're storing indirectly through a pointer, and this makes it kind of difficult both to understand what's going on and also to make sure we do a safe translation that takes account of this side effect. And both of these sorts of analyses are made more difficult by the presence of procedure calls, because what we have to do is trace the flow of values, not just through straight line code in one procedure, but basically trace it across a call into another procedure, through that procedure, and back again. And that sort of analysis is often costly, and actually is rarely done in modern, in existing commercial compilers, and we're trying to study methodologies for making it efficient enough so we can use it in modern compilers. So that's the compilation tab. The second place we want to use our side effect analysis is what I call semantics-based browsers. Now by this I mean we want to have a smart browser, so if someone is interested in enhancing a large software system, usually it has contained within the system some routines that that individual did not write. They were fetched from a library, or this is a combination of routines that have been accumulated over a large software project. And so that person really needs, if they're going to put in some statement as part of their enhancement, they're going to store a value in a particular variable, what they want to know is they want to be able to look forward in the code through using a smart browser and see all the places where that particular value can be used. Now, there aren't many software tools available today, but they're much more like cross-reference tables. They're really like, well, they're the kind of thing where if you click on a variable, they'll show you all the places in the program where that particular variable name is used. But that loses this semantic meaning of being able to click on a particular definition site and look forward to all the places where that value could be used, not just all the places where that name could be used. The cross-reference table approach is more like an index in a book, where if you turn to the index, it shows you all the places where a particular word is used, but has no semantic meaning in it, nothing about the context where you use that word. And then finally, we'd like to be able to use our side effects analysis to help build systems that enable us to keep a database of information about the definition and use of variables in a program as the program is evolving over time. So most people realize that even large software systems are not static objects. Code is enhanced, bugs are fixed, and we want the semantic information about definition and uses of variables to stay current with the current code in the system. And to do that, we have to have some kind of change analysis for that semantic information. So what have we actually accomplished in this sphere? Well, this has been our main research focus, as I mentioned, for a couple of years. And the work I'm talking about today is joint work with my co-PI on an NSF grant that's supporting this, Bill Landry from Siemens Corporate Research. And basically what we've done is we've designed two new algorithms for side effect analysis in the C language. And the interesting thing about these algorithms is they let us compare the trade-offs involved between the precision or the goodness of the information we actually get about the side effects, that is the small number of names that we can see at one of those indirect stores to a pointer is possibly the variable stored into, versus the cost of the analysis. So better precision of information involves more costly analyses, and I'll show you some of our empirical results to show you this. And we also, more recently now, and I'd like to invite you to go look at our program board out there, when we have several of them in our poster display, we've more recently been able to do experiments combining the two sorts of analyses and decomposing the program in such a way that we use the cheaper analysis on some parts of the program and the more expensive analysis on other parts. And the result has been that we get precise information that's just as precise as we got before with the expensive analysis, but the cost is more related to the cheaper analysis, and that's been an interesting experiment. And in addition, we've been designing an incremental method of doing these analyses, which would help us with the semantic change analysis. So I want to show you the kinds of empirical experimentation we have to do in our group in order to obtain these results. So basically, along the y-axis here, I have points in using the black algorithm, which is our more expensive, more precise algorithm, and the same data points for each program using the red or cheaper algorithm. The y-axis the x-axis is laid out from smaller programs to largest programs. And the size here is measured in terms of the number of nodes in our internal representation for the program. These programs vary in actual lines of code from 500 lines to 8,000 lines. And the y-axis here is showing us at one of those indirect assignment points that I've shown at the top here, the number of names that come back from our analysis as possible variables that experience a side effect. So if you look at the black data, you can see that on average across all the programs, about 1.5 names are reported as side effective as such a statement, which is pretty accurate. I mean, the lowest value you want to get back is 1. There has to be at least one variable that is experiencing side effects. So that means our analysis is doing pretty well. Now in the cheaper algorithm, the average is more like about 4 names. So you might ask, why bother with the cheaper algorithm? And the next slide shows you that nothing is free in this world. So here we're studying the same two algorithms. And again, the programs are laid out from smallest to largest. And here, on the y-axis, I'm expressing the time it takes to do the analysis of each program. And the time here is on a log scale. So actually, the vertical distances here are diminished because I'm charting them in logs. So for example, this program took 1/40th of the time with the cheaper algorithm as it did to analyze with the more expensive algorithm. Okay, so the vertical distances here are really diminished because we're showing them in log scale. And you can see that the cheaper algorithm is much, much less expensive, especially as the programs get bigger than the more expensive algorithm. So this is why we're really interested in this new technique of program decomposition, because that lets us combine cheaper analysis on some parts of the program with more expensive analysis on other parts of the program, and hopefully not incur the full cost of the expensive analysis. And initial studies have shown that this is the case. Okay, so that's a little bit about our program-specific side effect analysis. Now I want to talk about our analysis in C++. So this is a small program in C++, and you don't need C++ knowledge to be able to get something out of this example. So the idea in object orientation is you have various types of data in the program. Here I have 2 types, or classes, the base class and the derived class. And usually we try to code these programs in such a way that the types are related and they can share functionality or share operations. And also, very popular in object orientation is the use of a kind of functionality or operation that is referred to as dynamic binding, or in C++, the keyword is virtual. What virtual means here is down in the program where I use the function foo, because it has the word virtual in its definition, it means that I don't really know which function is being called down here. The program doesn't really figure out which foo function, whether it's the one in derived or the one in base, until execution time. So the binding of picking out which function really should be called there is based totally on whether or not Q is a base object or a derived object. Now this makes for a lot of flexibility in the kinds of things you can code in object-oriented style, but it also makes for a lot of work at execution time and slow execution. So our analyses are aimed at trying to come up with a better way of figuring out what small set of types Q could be at this point, and then enabling a better translation of this code, avoiding the runtime check insofar as it's possible, or at least making it a more efficient runtime check. So for example, in our analysis, we can see that at this statement, Q is created as a new type-based object, and therefore, when execution hits N9 here, we know that this has to be a call of this foo over here, the appropriate operation foo for the base object type. And when we go down inside of this foo operation, we can see that there's a new object of type base created called A inside of foo, and therefore, when we come back to the main program, we know that this second call, where we see A is calling a bar function, has to be the bar over here because we know A is a base object, not a derived object. So those are the kinds of information that we're able to derive from the C++ program, and C++ is just being used here as an example of the kind of an object-oriented language in which this dynamic binding takes place. So it's used in other object-oriented languages too. So we have some initial empirical results in this area, and I want to try to explain them to you with this chart. So we tested 19 programs, small C++ programs, varying in size up to about 500 lines of code. And in 13 of them, each one of these vertical bars represents a different program. In 13 of them, our analysis was able to identify at those virtual function calls the type of the function that was actually called. So we were able to convert those execution time calls into compile time translatable calls. And those are the calls that I'm looking at here. And what I want you to get out of this picture is that other people have put forward less expensive analyses that don't involve flow analysis, and they're represented, the calls that they could basically figure out and get to a unique resolution are the ones indicated in red and in yellow here. And all the other calls, which you see we were fully able to recognize with the techniques, with the bars that are black and blue, which is not on purpose, are the ones that our analysis was able to add into the programs as recognizable as being uniquely resolvable. So the point here is that our analysis gives qualitatively better information, at least on this small data set, than some of the previous analyses. Okay. And again, there's more detail about this project, as well as graduate students who can well explain them out by our poster. So our third project underway right now is the development of a unified software framework for all of our projects. So it became quite clear as we've been working in this area for a couple of years that what we really need is we really need to have some uniform foundation that all of our projects in these different sorts of analyses can build on top of. And so what we're doing now is we're taking a commercially available compiler for C and C++, and we're building an interface to it so we can reach into this compiler and take out the functionality that we need. And then these functions are what we're using in the basis analysis routines that are used in all these different kinds of analyses. Okay? So this gives us a way to base all of our analysis on some kernel set of routines, all of which never really interact with only one compiler, but rather interact through a unified framework here as an interface. The other thing that's nice about this, first of all, we're building this piece for the side effect analysis so as to release it publicly on the web in June, and this part of the development was sponsored by NSF money. But it also enables us to expand our analyses to other languages, because all we have to do is connect that language compiler to our interface, build the right interface functions, and now since all our analyses are coded totally in terms of the interface functions, they're basically portable across all the languages. So this has been an important step forward in terms of software engineering within the group. Well, I have another kind of analysis that I want you to look at outside. I'm getting the sign that we're done. So I just wanted to, the parallel analysis basically involves utilizing the power of a parallel machine, a small-scale parallel machine like an 8 to 16 processor desktop machine, which we're all going to have in a few years, according to Ken Kennedy and others, and utilizing that to do analysis work. So it is a parallel algorithm for analysis, not a parallelizing algorithm. Anyway, these are the current members of our research group, and many of them are here today and we'll be glad to answer your questions. And so our focus is on trying to see just how much information about the meaning of the program we can sort of squeeze out of it at translation time.